Okay, I think it's recording now. So if you all see the screen, then where we left off last time was this chapter 3 from Bhuvan's book. In particular, we had this proposition that says the following. So if we have a sub Riemannian manifold M of space E, and we endow it with the metric induced in the space E, so the same metric from the space M for the manifold, and we have a smooth function, then the Riemannian gradient can be computed by just taking the regular gradient, where f bar would be just like a smooth extension of the function f. We compute its gradient, and then we project on the tangent space, basically this vector. Okay, and this actually relates. There's in the book. There's a counter example right after this. This relates to a question that Jose asked last time. It's basically boils down to manifolds whose local inner products are not the same as those of the vector space. Okay, so in particular, for instance, we will be working here on the relative interior of the probability simplex, right? So we're in RD space. We're looking at vectors with strictly positive coordinates that sum up to 1. So this manifold looks like this. It's just like the interior of the set. And this is an manifold which is embedded in RD. Okay. So it is I don't know here the exact language. I think we can call this a submanifold of RD. We also show that it's a Riemannian manifold, but it's not going to be a Riemannian submanifold. Okay, in the sense that the inner product is changing over the space. Okay, at every given point x, the tangent manifold is always the same, right? Because this is basically this is a relatively open set. So basically, when I look at any point, its local structure is basically that of an affine space, and therefore it has just like a normal direction. That normal direction defines what's the tangent space at every given point, and it's the same regardless of which point x I'm looking at. And you can define this different inner product, right? So this is a distorted inner product where you just take the regular inner product, but every term that contributes to the sum is kind of rescaled by this 1 over xj. Okay, this is called the Fisher-Rao metric, and it defines Riemannian manifold over M. Okay, that I'm not going to prove that's an exercise. And the question is, like, can we, given a smooth function f, compute its Riemannian gradient, right? So can we compute grad f? And when I say computing grad f, I mean it in terms of computing it in terms of kind of the Euclidean gradient of its natural extension over the space. So maybe this is a good point to ask whether what I'm asking here is clear, or if there are questions. Okay, so if there are no questions, let's try to work this out. We'll get to a formula. Okay. Let's first consider any point in the tangent space, namely it's defined by this linear equation, right? The sum of the coordinates equal to 0. And I will denote this grad f bar as the Euclidean gradient of the extension of f, right? And we will just use the definition of what this Riemannian gradient means, namely that whenever I take inner product of this vector with a vector on the tangent space, and I use the local metric, this corresponds to the evaluation of the differential of the function in the direction v, right? Since this is an object which is perfectly defined on Euclidean space, right? I can make this identification of f with its extension, and therefore I will get now this identity that involves the extension of f. Now, this we know from second year calculus that corresponds to, like, the Euclidean gradient is precisely defined by how the differential operates on any vectoring space, right? So this evaluation of the differential would correspond to the inner product of f bar, or sorry, gradient of f bar with direction v, but now not in the local metric, but in the standard Euclidean metric, okay? And the question is, like, how do I relate these two, right? I mean, this is the local and the non-local, the standard metric. And for this, we just multiply and divide by xj, right? This way we get this kind of distorted inner product, but this now tells me what are the coordinates of my Riemannian gradients, right? So I can identify this summation over here as an inner product of the vector v with some vector g on the local metric x. Now, what is this vector g? It's just like a rescaling of the Euclidean gradient by multiplying by the coordinates. So that means that I can represent the gradient of the Riemannian gradient of f in terms of the Euclidean gradient by rescaling with the respective coordinates. Okay. And this shows that this previous formula that I showed in the beginning, that one involving this kind of Euclidean projection, doesn't work anymore because we're not working on the endowed metric of the space anymore. Okay. So I hope the example is clear, but if not, now it's a good time for taking questions. No questions?
One, sorry.
Mm-hmm.
But if you don't change the inner product, the x inner product, and you keep the other one.
No, yeah. If we would be using the Euclidean, do you mean if I would be using this inner product?
Yeah, because
one of the vector space.
Yeah, in the computations you passed by the classical inner product. Actually, you use the gradient of the.
Exactly. Yes. Yes.
Yeah. Then in that case, the formula holds. No.
No, this is all these steps are valid, right? The point is, like, you're trying to identify this object, and the way we identify it is by how it acts on different vectors, right? So we need an identity in the end that involves this local inner product. That's kind of the point of these steps, right? This is definitely true, and it's always true.
Okay. Then I didn't get why. What is the problem? What's the counter example actually?
Well, so the first proposition, this one comes from the previous presentation. Okay, this is from last time.
Yeah, I remember that identity.
Yes, and the point is, this projection that I'm referring to here is just the Euclidean projection onto the tangent space.
Yeah.
So that's definitely is definitely not what's happening here, right? So this vector f might or might not be on the tangent space. You're not even just like projecting it, but you're distorting it.
Yeah, but by multiplying by xj, you are not projecting onto the. Okay, I got it.
Yeah. So and I hope I did this. This was an exercise from the book, so I hope I did it correctly. But if anybody sees a mistake, feel free to step in.
Yeah, because the projection on the tangent space, into the tangent space should be just the.
It's gonna be projecting into this this.
Yeah, then you have to subtract the mean, actually, the mean of the vector.
Yes.
That's the way in which you project, that's why it's different. Okay.
And yeah, maybe somehow that's also needs to be done here.
Okay.
Because this grad f should also be on the tangent space. So I mean, this inner product is defined over the tangent space. So maybe that's still missing. I'll leave it as a question. I hope I can find it later, but this should be, I think, minus the summation. I would bet because of what you're saying, right? I mean, this thing must lie in the tangent space. So we need to make this correction. But okay, I'll think about it. Thanks, Luis. Okay, so yeah, that's basically just a distinction between embedded metrics and these like more general distorted metrics. Okay, but actually what we wanted to cover today is go into the algorithmic part. So we want to design optimization methods to minimize a function, a smooth function defined on a manifold. Okay. And kind of the approach that we'll take, at least in this chapter, is that of a Riemannian gradient descent type of algorithm. Okay, so it will be like an analog of what we know for gradient descent, but applied to the manifold. And I mean, the story behind gradient descent is something quite intuitive. It's basically just leveraging Taylor expansions, right, to understand how we can certify decrease of the objective by an iterative method. So now we want to do the same, but since we're in a manifold, we need to work with curves and whatnot. Okay, so first let's consider a curve that basically passes through point X with a certain velocity v, which is in the tangent space. And we'll consider this parameterized curve as such that it contains an open interval of the real line that contains zero, right? So basically, we have X. This is our curve C, and the tangent direction is V. Okay. Now we want to understand basically if we're maybe, we want to come up with notions such as critical points and first order optimality conditions in the same way that we did in the Euclidean space. And the whole point is that if we're working with a function f, which is a smooth, whenever we take a parameterized curve, the composition will also be smooth, right? And this will be something that is defined on the real line, so we can basically reduce to the real case in terms of establishing critical point conditions. Okay, so we will now use just the Euclidean Taylor theorem from, just the first year Taylor theorem, right? We'll expand this function g. The precise form of the error term, it's really up to you in terms of what do you want to assume. But given the assumptions of the book, I think you can get here big O of t squared. Okay. And this is a real function g. Now we want to relate it to f and its gradients and so on. So now let's get back to that. I mean, g prime of t just by the chain rule is going to be the differential of f evaluated on the point zt, and then that differential will be evaluated on direction c prime of t. And if we take t equals 0, we know that this c of t is x and the c prime of t is v, right? So, and we also know that this evaluation of the differential in the manifold can be expressed in this way, right? It's going to be grad f at x inner product v in the local metric ct. And when t is equal to 0, this is going to be x as well. So in the end, you just get a formula for the derivative based on the gradient of f. And if we replace that into this expression here, we end up with something which now looks more related to the function f. Namely, when I take this parameterized curve, right, I have a Taylor expansion that involves the function evaluated on the curve is equal to f of x plus t gradient of f comma v. That this is what we just proved, right? The linear term t here comes from here, and then we have this quadratic error term. Also, we can establish this equivalently, but instead of using the parameterization of curves, we can use retractions, right? Now we can think of points on the tangent space, and those points are kind of mapped back into the manifold using a retraction. And if we do that, this can be written in a slightly different form, right? Now it's going to be f of the retraction for some displacement s. That's going to be equal to f of x. The linear term looks the same, but now remember we're plugging in this t as part of the displacement s. And then our quadratic error now will become something that depends on the norm of S with respect to the local metric X. Okay. Yeah, and we saw this last time, but they sort of reiterated in the book that this kind of composition of the function with the retraction is called the pullback, because it's basically taking points in the tangent space, which might look like this, and sort of pulling them back to the manifold. Okay, and basically you can see it, right? Now that we have this, we can start writing things like stationarity conditions and so on. Here's an exercise that I will not prove. This seems a pretty direct consequence of the I mean, this is like the sort of Taylor expansion without error sort of thing. So it says the following: if you have a curve going from 0, 1 to the manifold with z of 0 equals x and z of 1 equals y, prove that there exists some t which is strictly between 0 and 1, such that f of y is equal to f of x plus the gradient, and then this sort of first order term is evaluated at some intermediate point in the curve.
Like the mean value, no? Theorem, something like that.
It's like mean value, but also isn't there like an exact version of Taylor that you sort of keep the last term in the expansion with like an intermediate point, which is I mean, it's somewhere in the interval, or?
Yeah, I think it follows from the same, I guess.
It's all the same. Yeah, exactly.
The mean value theorem, I guess. Yeah.
Right, and I can believe this is true because of what we just said before, right? Everything reduces to some kind of one-dimensional calculus problem. So, and I just kept it here because apparently they need it later, but it's not a big deal for what we'll discuss today. Okay, so let's look into optimality conditions. And yeah, we'll just use the standard, or more or less a standard notion of critical point. So given a function f over the manifold, which is a smooth, we will say that x, it's a critical point if whenever a curve passes through x at time 0, if you take f, you compose it with a curve and take the derivative at 0, you get something which is non-negative. We would actually like to say maybe that this is equal to 0. And that's completely equivalent, because whenever you have a parameterized curve that contains 0, you can just basically take the reverse parameterization, or basically reverse time, and then you would get the analog conclusion in the opposite direction. So you can basically prove that this non-negativity of the derivative is the same as just assuming that it's 0. And yeah, and now we're going to prove that also this kind of, I'm sorry, this is just straightforward, but now we're going to prove that corresponds to the more standard optimality conditions or critical point conditions we studied in calculus. Okay. Oh, sorry, I'm completely wrong. Let me think. Yeah, no, this thing is at least intuitive, but we'll prove it, I think, in the next proposition. Okay. So the proposition says the following. This is like a Fermat's condition. Every critical point of a smooth function f, every local minima of a smooth function f, it's a critical point. Okay. Okay, so how do we prove this? We start first from this local minima condition, which, remember that in the manifold, you always can have a neighborhood of, yeah, every point will be, yeah, I mean, it's, what do I want to say? It's the topology over the manifold can be obtained by taking open balls, for instance, I mean, or at least a base of neighborhoods, and intersected with the manifold, right? So, yeah, if you're in a local minima, what you can assume is that there's going to exist an open set. And this open set is an open set in the manifold, but that means open set intersected with the manifold, such that every point in this open set is such that the value of the function is greater than or equal to f of x. Okay. And by contradiction, we will assume that there exists a curve that violates the critical point condition, right? So when I take the composition of f with the derivative, with f with the curve, I take the derivative at 0, I get something negative. And I mean, this is basically the first year calculus proof. What we'll do is, by continuity of this thing, this is not only true at 0, but it's going to be true in a strictly positive interval that contains 0. So this negativity of the derivative holds for some non-negligible interval. And now we use the fundamental theorem of calculus to say that f of the curve is equal to f of z of 0, which is just x, right? Then you get the integration of the derivative that on this like sufficiently small interval, we know it's always negative, and therefore you will have, in fact, you will have a strict inequality here. And as I also said, this z of 0 is just x, right?
Yeah, I guess for the strict, I guess you have to take a small minus epsilon probably, and to keep it in a neighborhood or something like that, because of
You mean for this condition?
Yeah, I'm saying that because you have already that the derivative at 0 is clearly negative, then let's say minus epsilon. And for continuity, you can take a delta in which is at least minus epsilon half.
Ah, okay.
And that you are sure that you are strictly minimum, because in the integral probably you can, for the limits.
Yeah, I see. You want to say here negative epsilon or something.
Something like that, yeah, probably for sure. The negative, yeah. But it's just a detail, I guess.
Yeah, let's do that.
Yeah, so just a detail.
I mean, I guess what's going to happen is that you have to say this derivative is equal, or we can define it as like minus epsilon. And then we can say that there's an open interval where you're strictly below half epsilon. And yeah, then we can use this upper bound. Fair enough. Thanks. Okay, and so on one hand, we have that the curve is going to lie to, or is going to reach strictly smaller values than f of x. So this should be immediately a contradiction, but let's be more careful about how to conclude this. I mean, it should be a contradiction with this, right? At least intuitively, because the curve should somehow intersect this open set. But now we need to prove that. And we'll use these like basic facts of topology, because the topology is a bit funny, right? I mean, since C is a continuous function, the pre-image of this U set that we define here, which is an open set, must be an open set. And it also contains 0 because we said that Z of 0 is X. And therefore, these two sets would intersect non-trivially. And that's basically the contradiction, right? Because we'll get that there is some positive t where C of t belongs to U. And therefore, f of ct has to be greater than or equal than f of x. That's a contradiction with what we just proved here. Okay. So modulo this like the fact that we're working in a slightly non-standard topology, this is straightforward. Okay. Okay, and now we have the following proposition. So we have again a smooth function over the manifold M, which is a Riemannian manifold. And why I assume Riemannian manifold? So I can make sense of the gradient. Okay. And basically what we'll prove is that every critical point corresponds to a point whose remaining gradient is equal to 0. Okay. So this is also pretty easy. Let's consider a curve C that passes through x at 0 and whose derivative is some v in the tangent manifold, then the derivative of the composition at 0 is going to be the differential of f at direction v. And we also said that the remaining gradient is precisely defined by this identity, right? So now that we have this identity and we know that critical points are such that this thing is non-negative or is equal to 0, right? We can get it. Let's first do this implication over here, right? So if the gradient of f is equal to 0, clearly this thing was going to be equal to 0, and this is going to imply that the derivative of the composition is equal to 0, which implies, of course, that x is a critical point. And on the other way, if we assume that these derivatives are always non-negative, now we take a curve C that passes through x. Let me think. Yeah, because of this identity, we can always say, I mean, take any point in the tangent space, right? Now take a curve that sort of passes through x and has derivative at 0 equals to that v. And now you use this identity, right? And you will have that this inner product of the gradient with direction v is non-negative. And this is going to hold for every v such that you can construct this curve. And those are exactly the points on the tangent space. Okay. Now, since the tangent space is a subspace of, is a vector space, right? Whenever you have a vector, you have its negative. So this non-negativity condition is equal to just being equal to 0 for every vector in the tangent manifold. And since you have an inner product with all possible vectors being equal to 0, that implies that the remaining gradient is equal to 0. Okay. So any questions about this? Or?
I have a question.
Sure, go ahead.
Why that curve exists?
Why that? Why what?
That curve exists.
Ah, good question. Well, I mean, the tangent manifold is defined precisely by those curves that, I mean, correct me if I'm wrong, you know more about this than I. So I think that the tangent manifold is defined by the derivatives of curves that go through 0, right? And you take the sort of the vector space generated by those directions, isn't it?
Okay, yes.
So if that's correct, then this is straightforward, because by definition, if a vector is in the tangent space, there exists a curve such that.
Yeah.
Okay.
It's because there are a lot of definition.
Yeah. No, I mean, it's
so
it's actually confusing. So
yeah.
Okay. Good. So
I have another question. Sorry, that is probably even more basic. It's about the product space X in the tangent space. Can you recall me the definition
of the tangent space?
No, the inner product. The
inner product. This is something you define. I mean, this inner product. Let me take some space. So we were working in the beginning with manifolds M, right? On some vector space. We didn't endow it with a metric immediately, but we said last time that you can always define, I mean, if you have an inner product for every point X, the only thing that you want to assume is that this is a smooth function. So this goes from it takes vectors in the tangent space and maps it through the real line. It must be an inner product. On the tangent space. That's the first requirement. And the second requirement is that it's smooth. Okay, and this smoothness requirement is based on, I think, if you take curves on this side and on this side, right, then you will have a function which goes from the reals to the reals.
Okay.
And
okay.
You want that function to be smooth.
Then any inner product satisfying that can be used for our purpose.
this whole thing implies or is the definition of a Riemannian manifold.
Okay, thank you.
Yeah.
Thank you.
But please, anybody can correct me if I'm wrong here. I think that actually this is maybe not the only definition. There's like a couple of ways to get to it. I think that somebody made a comment about this last time. Maybe Agustin. I don't know. This came up either 1 or 2 weeks ago. Okay. Yeah, this is where we were. Right. Okay, so now we'll get to the algorithm, right? So what we want to do is sort of get or come up with like a non-Euclidean version of the gradient descent. Okay, gradient descent is just we start from some point in the vector space and we iterate this thing, right? So you're at some point xk. You compute the gradient of the function at that point. You choose your favorite step size and you basically displace by that much. And sort of the intuition behind doing this is that, you know, if I have a function like this, right? And if I step at any given point, the negative gradient of the function gives me the steepest descent direction, right? So it makes sense that at least if I pick this step size sufficiently small, I should always be guaranteeing that the function decreases unless I'm already at a critical point. And if I am at a critical point, I'm in a fixed point of this iteration. I got to where I wanted to reach. I mean, not necessarily, of course, but basically I cannot do much at that point. Riemannian gradient descent would be a natural translation of that, where, of course, we need to now move through the manifold. So we need to be more careful about how to do this displacement that we were doing just linearly there. And what we will leverage here is the fact that when we are in a Riemannian manifold, this grad f is something that lies in the tangent space. And therefore, I can do a retraction. Right? So if I have a retraction and if I'm able to compute gradients, I can do something at least intuitively similar to what gradient descent does. Okay. And the main algorithmic questions we need to answer for this to work is how do we choose the step size, right? And here, basically, this is not going to be too different from what we know from classical optimization. The sort of tools and techniques to do this is what people call line search, right? So line search is just like some method to come up with a choice of alpha that guarantees convergence or some kind of progress at every iteration. So morally, you know, given a certain point xk where I'm at, what I would like to do, for instance, would be maybe to compute the step size that gives me the highest amount of progress, which would be, for instance, just minimizing this sort of one directional version of the objective, right? So for every choice of t, I can maybe make a decrease or even make things worse. But basically, when I'm minimizing, I'm doing the best that I can when I follow this direction of the negative gradient. There are a few possible strategies that we can do here. One of them is just choosing a fixed step size. The second one would be to kind of optimally solve this sub-problem at every step, which usually is rather intractable. We cannot do this in general. And the smartest choice that people do is the so-called backtracking. So backtracking is basically a way to solve this thing approximately, starting from a guess T0 of the step size, verifying whether it satisfies a sufficient decrease condition that we will specify later. And if it doesn't, we just reduce the step size by a constant factor. So we will be basically exponentially decreasing our guess of t until our condition is satisfied. Since we said that negative gradient gives me the steepest descent, I can hope that at some point I get the sufficient decrease I'm looking for. Okay. So this is what we'll specify later. Sufficient decrease is going to be what's going to drive or what's going to make the choice of what's the backtracking parameter in the end, or rather how I'm going to update the t's at every iteration. Okay, So for what we'll do now is I will prove a fairly general version of convergence guarantees for critical points for this Riemannian gradient descent. What we will do here is a complete analog of what it's done in Euclidean space. There's almost nothing different going on. And for this, we will just make a couple of assumptions that are also standard in Euclidean optimization, okay? First of all, we will assume that we have access to a lower bound, a global lower bound for the function f over the whole manifold. So lower boundedness is usually a condition that we need for these optimization methods to work. I mean, if the function is not bounded below, the optimum is probably negative infinity, and then there's basically not much of a point in doing optimization anyways. And the second condition is that this is the sufficient decrease thing I was referring to. So what we want to ensure, I mean, you have to sort of interpret correctly what this means, this thing about sufficient decrease, right? Maybe I would like to say that at every step, I decrease as much as negative h, where I fix on h. But that's not always going to be possible, especially when I'm close to the optimum, right? So this sufficient decrease should be something that tells me that I'm decreasing my objective value into something that also decreases as I'm approaching the optimal solution. And one very natural thing to say is, for instance, that my decrease is always lower bounded by something which is proportional to the gradient squared, right? So as I'm approaching the optimal solution, this becomes small, and therefore this becomes small, but things are sort of in the right scaling. Okay.
Just a question, what should be that norm there of the gradient?
Great question. This should be the local norm.
Okay.
Yes.
I think we're gonna see this, or isn't. I think it is. I think in the book, in this chapter, they say we're gonna omit the sub x whenever it's clear from the context.
Okay.
So I think the proof also doesn't have it, but that doesn't mean that it's just a standard norm.
Yeah, because if the gradient is in the whole space or in the whole RD, let's say, probably you are not minimizing.
Not at all. Yeah. No, this is the local norm. Yeah.
Okay.
Thanks for catching that.
Right.
Yeah. Okay. So and this is kind of what I said is the classical theorem about convergence to stationary points for gradient descent. We'll consider a function which is smooth over a manifold and satisfy this lower bound condition, okay, over the manifold. And we will assume that the algorithm we use generates a sequence of points that satisfies this sufficient decrease condition with some constant c, okay? If those two things hold true, then we can prove that the Riemannian gradient of f for the sequence converges to 0 as k goes to infinity. And in particular, any accumulation point of the sequence is going to be a critical point. That's also not a straightforward statement. We need to prove it. And you also have this sort of algorithmic upper bound, or like a complexity upper bound. So for every capital K you fix, there exists some kind of intermediate iterate which achieves a norm of the gradient which decreases with a rate 1 over square root of capital K. Okay, this is just like a normalization factor if you want. But basically the rate at which you can observe smaller and smaller gradients is going to be like 1 over root of your number of steps. Okay. So before moving forward, are there any questions about this statement? No? Okay. So yeah, if you have ever seen this proof, this is going to be exactly the same as the classical proof. And it is based on a telescopic argument. Okay, so first of all, we start by writing this, f of x0 minus your lower bound. Okay, since this is a lower bound, this is smaller than anything you can write down. And in particular here, I'm going to pick the last iterate of the algorithm. I'm sorry that my capital K and small k look very similar, but this thing over here is the last iterate. Okay. So I have first iterate minus last iterate. Of course, I can write it down as a telescopic sum involving all consecutive terms. And here I'm going to use the sufficient decrease condition to lower bound each of these things. This is the progress, right? And my lower bounding it by the total number of iterations times this given constant and the minimum norm of the gradient that I observed, right? So notice that each of these things is lower bounded by C times norm of the gradient. Like that, right? And what I'm doing is just lower bounding all these gradients by the best one I can observe. And that's what gives this extra capital K factor here. Okay, so you can see it here, right? If I take K going to infinity, I can see that this sequence of minima necessarily has to go down to 0. But that's not what I said. I said something stronger. I said that the limits of the norms of the gradients go to 0. So I need to make an extra step. Okay, so let's now prove this first statement. Because of the sufficient decrease condition, I have in particular that the sequence of iterates is decreasing in objective value. Okay. And therefore, when I write down this lower bound that I wrote here, I can take the limit of capital K going to infinity because there's an upper bound here. Okay, and it's a sequence of non-negative numbers, so I can get this series from K equals 0 to infinity of the consecutive difference of the iterates. And since this is a convergent sequence, in particular, the summands of this series have to go down to 0. Okay. And now I'm in business because I can say, okay, 0 is the limit of the consecutive function values of the iterations. And because of this assumption that we have about the sufficient decrease, we can lower bound this by the norm of the gradient. So I can maybe, to be fully formal, I can take here the lim sup of K goes to infinity. But since it's going down to 0, I can get the convergence. Okay. Now for the second part, take any x which is an accumulation point of the sequence. That means that there is a subsequence that converges to it, right? And we already proved that 0 is the limit of the norms of the gradients over the sequence. That's the same limit for the subsequence. Now we can use continuity of the norm and continuity of the gradient and so on to kind of pull inside this limit. And therefore, I have that the norm of the gradient of f of x is equal to 0. Although I just noticed, because of what we said, that there's a small catch here. Because here, for instance, you have xk, you have xkn, and the question is like, what do you have here? But I mean, continuity should say that. I mean, it's not that I'm pulling inside this limit, but rather we can use continuity in this way. And when I say continuity, I'm using continuity of f, of the gradient, and of the local metric. So all those things composed are continuous.
Yeah, probably something like boundedness of the gradient plus the continuity of the inner product.
I mean, yeah, it's true that it's bounded because it goes down to 0.
Yeah.
But what I'm just saying here is like, this thing is a convergent sequence, right? This xkn. So you can look at this whole thing, this whole thing as a function of x. And what I'm saying is like, as a function of x, this is a continuous function.
Yeah. And about that, sorry, what is the assumption on f for being the gradient of f also continuous? You have C1 on the manifold or something like that, or?
I think so. I mean, they say smooth, so maybe even infinity. I mean, it's I don't remember what's explicitly said in the book. I think that for all these arguments, C1 suffices. That's the kind of smoothness that you need. But I would bet that they were even assuming like all sorts of derivatives are continuous.
And just another question, because there is for the constant step size approach that you told us before, usually you need something like Lipschitz continuity of the gradient or something like that. Does that even exist in the Riemannian concept?
Yes.
Yeah? Okay.
So, I mean, I think this is the end of my, this is the end of what I prepared. But right after this, they go into complexity bounds. So there is kind of, there is some kind of definition of what it means to be, for instance, Lipschitz and all that, which I didn't get to see. So I guess we'll see it next time. But right, the point is like all these complexity bounds will hold under such assumptions. So there's like particular complexity classes and particular step sizes that are tuned for that. So actually, I guess we'll have to decide now who's going to be presenting next.
Okay.